Let's learn about the importance of vaccination. While a vast majority of parents get their children vaccinated, very few know how they work, and some are skeptical. Over the past 50 years, immunization has saved millions of lives and made once common diseases like measles, rubella, tetanus, hepatitis B, mumps, and pertussis relatively rare. Vaccination protects you and your loved ones from serious illness and complications from those illnesses, such as hearing loss, seizures, brain damage, and death. Not vaccinating your kids puts them at risk for all of these things, but it also puts countless other people at risk as well. If your child isn't immune, they are capable of spreading disease to other people who have weak immune systems, aren't vaccinated, or are too young to be vaccinated. Contracting one of these diseases not only has the potential to kill those who can't be vaccinated, infants and people who are immunocompromised, but could also cause an outbreak. An outbreak is a cluster of cases of a particular disease within a community. Outbreaks and epidemics caused by unvaccinated individuals are becoming more and more common. For example, one person with measles who didn't yet know they were sick at Disney's Magic Kingdom recently started an outbreak that spread across half of the United States and infected 189 people. There was no magic that caused this disease to spread so fast and so wide. It happened because people were unvaccinated, and measles is extremely contagious. Measles has been declared eliminated in the US in 2000. But now it's back. To keep deadly diseases from returning and spreading, we need to have enough people vaccinated to act like a force field. Those that are immune surround an infected individual and prevent the disease from taking hold in a community. It is everyone's responsibility to prevent measles and other diseases from turning the happiest place on earth into the home base of a dangerous outbreak. Vaccines are safe and effective. They may not be magic, but they'll protect you and your loved ones. We are a community. We vaccinate to protect. #immunity in your community.
Throughout history, we have developed vaccination to protect both humans and animals from a wide range of preventable and potentially serious illnesses. With vaccines, we take advantage of one of the most important aspects of the immune system, the ability to develop immunological memory. This means that once the person or animal is exposed to a particular pathogen, in other words, anything that can cause an illness, they will develop resistance to infection with the same pathogen in the future. Our adaptive immune system contains white blood cells known as T and B lymphocytes. These become activated during the first time or primary exposure to a pathogen. Once the pathogen has been fought off by our body, a population of these T and B lymphocytes, known as memory cells, remain in the individual. These memory cells remain on standby, ready to react quickly when the individual is re-exposed to that particular pathogen in what is known as secondary exposure. The immunological memory helps the immune system respond much more rapidly and effectively than during the primary exposure. As a result, the individual is generally protected from the development of disease symptoms. Now that we know about immunological memory, what about vaccines? Well, it simply means that we generate this memory effect artificially and at an early stage to prevent future disease. This means we inject a weakened version of pathogens, inactive pathogens, or just particular parts of pathogens into the individual we want to protect. In healthy individuals, these vaccine components activate a specific immune response, mimicking primary infection, but weak enough not to cause the development of disease symptoms. For example, the varicella or chickenpox vaccine involves injection of a weakened version of the varicella zoster virus. In healthy individuals, this weakened virus will not cause chickenpox symptoms, but it will activate an immune response. As a result, when the vaccinated individual comes across the varicella zoster virus again, for example from a person infected with chickenpox, he or she will mount a rapid memory immune response to the virus and will not develop chickenpox symptoms. By taking advantage of immunological memory in this way, vaccination prevents and controls the spread of a wide range of illnesses, including polio, smallpox, whooping cough, measles, and the seasonal influenza virus. In recent years, there has been controversy over the safety of vaccination programs. To date, All credible scientific evidence strongly supports the importance of vaccination in avoiding preventable illness in individuals and populations. So there you have it, vaccinations. They trigger our immune system to develop memory cells ahead of time, meaning our immune system is ready to launch an attack as soon as a pathogen enters the body.
This animation shows how the levels of immunoglobulins change during the specific, adaptive immune response that develops as a result of infection with a pathogen or following immunization. When vaccine antigen enters the body, it triggers an inflammatory reaction. This is initially mediated by the non-specific innate immune system, but subsequently develops to involve the specific adaptive immune system too. Dendritic cells are attracted to the antigen. The antigens are taken up by the dendritic cells, also known as antigen-presenting cells, and presented on the cell surface membrane. They migrate to the lymph nodes. The primary specific adaptive immune response is now underway. T cells that recognize the specific antigen being presented by the dendritic cell bind to the antigen. This process activates the T cell to become a helper T cell. Meanwhile, immature B cells pick up the antigen on their surface immunoglobulins and process it. Once processed, the antigen is presented on the surface of the B cell. There are approximately 10 million different types of immature B cells. Each cell carries a unique immunoglobulin on its surface that can bind to only one specific antigen. The helper T cell binds to the antigen on the B cell and then releases cytokines that stimulate the B cell. Once stimulated, B cells undergo rapid proliferation and differentiation into plasma cells and memory B cells. One such B cell can produce thousands of daughter cells in a few days. This action increases the capacity to produce stronger binding, soluble antibodies. The antibody concentration rises in the blood serum. Further stimulation of B cells by T cell action leads to affinity maturation, where high-affinity antibodies are produced. The concentration of antibodies is now at a peak. Infection is over. The plasma cells die off and the antibody concentration falls. This is known as the contraction phase. The specific adaptive immune system retains memory of the antigen for future use. Memory B cells remain in bone marrow and may circulate between lymph nodes, ready to recognize the antigen again if it presents itself. They continue to secrete a low level of high-affinity antibodies. This is known as immunological memory. When the body is exposed to the same antigen again, these high-affinity antibodies in the blood bind to the antigen. This acts as a signal to circulating cells that recognize the antigen quickly, and the secondary response begins. Memory B cells and T cells are activated more rapidly than on primary contact with the antigen, as the antigen is already familiar to the immune system. The memory B cells proliferate and differentiate into plasma cells that produce high-affinity antibodies in higher concentration than found in the primary response. Often, during the secondary response, further maturation occurs, leading to the antibodies that are more specific. Consequently, each time the body is exposed to a particular pathogen, the antibody response becomes quicker, more sustained, and of higher affinity, offering even better immunological protection.